Welcome to today's Explainer. We're diving straight into a real masterclass on relay logic control, or RLC for short. If you've ever looked at massive automated systems and thought, how does all that actually work? Well, you are in exactly the right place. RLC is literally the foundation of it all. It's the bedrock. And here's the best part. Once you wrap your head around this, making the jump to programmable logic controllers, PLCs, becomes incredibly easy. It's like unlocking a cheat code for industrial automation.
But before we get tangled up in wires and switches, just think about this for a second. How exactly do you safely start a massive, heavy-duty industrial motor without instantly causing a catastrophic voltage drop across your entire grid? Think of it like trying to push a heavy car from a dead stop. Getting it rolling takes a massive surge of initial energy, right? Controlling that enormous rush of power safely and knowing exactly how to start these beasts is exactly the puzzle we're going to solve today.
So, here is our complete syllabus for this session. We'll start with Introduction and Basics, then move to Hardware Components. Next, we've got Logic Gates and Control Logic, followed by Practical Circuit Design. Then we'll cover Drawing and Simulation, and wrap it all up with Troubleshooting and Safety. Simple, chronological, and step-by-step. Let's get into it.
All right, kicking things off with sections 1 and 2, Basics and Hardware Components, because you really can't build the system until you know the puzzle pieces, right?
Meet our absolute heavyweight champion of the hardware world, the magnetic contactor. Now, it's crucial to understand that this is totally distinct from your standard everyday relay. While smaller relays might handle the brainwork, your control circuit logic, the magnetic contactor is the muscle. It sits directly on the power line to handle that main, incredibly heavy load, like a giant industrial motor.
Of course, the contactor doesn't work alone. It operates alongside an essential hardware toolkit. We've got push buttons with normally open and normally closed contacts. We have those standard relays and timers we mentioned, including on-delay, off-delay, and cyclic timers. For keeping things from blowing up, we rely on protection devices like circuit breakers and overload relays. And finally, we have inputs to tell the system what's happening, like proximity sensors, photoelectric sensors, and limit switches. These physical devices are literally the nuts and bolts of your control and power circuits.
Moving right along to Section 4, Practical Circuit Design, and we are starting with the Direct Online, or DOL, starter. The Direct Online starter is far and away the simplest, most widely used method to fire up a three-phase induction motor. It applies full-line voltage straight to the machine. Here's how the sequence goes. First, you press the green, normally open start button, which shoots power straight to the contactor's coil. That coil energizes, powerfully pulling the main poles together to crank the motor. Now, to keep it running when you let go of that button, an auxiliary normally open contact runs parallel to the start switch. This is a brilliant little trick called latching. Finally, pressing the red normally closed stop button simply breaks the electrical loop, de-energizes the coil, and stops the motor dead.
Now, while the DOL starter is super easy to design and gives you incredibly high starting torque, it comes with a major catch. Remember that heavy car analogy? At the exact moment of starting, the motor greedily draws 5 to 7 times its normal running current. That massive inrush current can literally drag down the voltage across your whole power line. Because of that heavy hit, DOL starters are almost never recommended for larger motors, specifically anything above 5 horsepower.
So, what do we do for the big guys? Still in Section 4, let's look at the escalating solution, the Star-Delta starter.
For those massive three-phase induction motors over 5 horsepower, the Star-Delta starter is standard industrial practice. You literally have to use it. Unlike the DOL method, a Star-Delta starter completely avoids slamming the motor with full-line voltage right out of the gate. Instead, it cleverly reduces the voltage during that initial startup phase. This eases the motor into rolling safely, effectively choking that massive full-load current so it doesn't wreck your electrical system. It's an absolute lifesaver for the grid.
Stepping back for a second to Section 3 of our syllabus, let's peek under the hood at the underlying logic driving these starters. Believe it or not, using nothing but simple relays and switches, you can manually construct fundamental logic gates. We're talking AND, OR, NOT, and even XOR gates. You also employ genius control mechanisms, like latching, which we just saw in action with the DOL starter, where a circuit physically holds itself on even after you take your finger off the button.
And you really can't talk about logic without mentioning interlocking. The definition is simple, but it is absolutely critical for safety. Interlocking is a hardwired setup ensuring that 2 magnetic contactors literally cannot snap shut at the exact same time. Think about a forward and reverse motor circuit. If you accidentally activated both directions simultaneously, boom, catastrophic short circuit.
Interlocking is your ultimate insurance policy against that.
That naturally brings us to Section 6, Troubleshooting and Safety.
Whenever you're designing or fixing these systems, safety has to be your absolute #1 priority. You've got to know your way around a multimeter, testing for continuity, voltage, and current to hunt down annoying loose connections or sliced cables. But listen, before you even touch a wire, you must adhere strictly to industrial safety rules. The big one is the lockout, tagout, or LOTO process. You have to physically lock and tag those live lines to ensure they are dead before anyone puts their hands anywhere near them. No shortcuts here, ever.
Finally, rounding out our syllabus is Section 5, Drawing and Simulation.
Long before you wire up a physical 50-horsepower setup, you really need to learn how to read industrial circuit diagrams. You need to know those symbols like the back of your hand. Then, you jump into simulation software on your computer, like CADE-Simu or PC-Simu. This is the ultimate practice ground. You can digitally test your latching, interlocking, and timer logic in a totally safe environment. Making a wiring mistake here just means hitting reset. Making a mistake on the factory floor? That's a dangerous, expensive short circuit.
So, if there's one core takeaway from this entire explainer, it's this. Relay logic control really is the bedrock of industrial automation. It's the beating heart. If you actually take the time to master these physical wire loops, control circuits, and safety protocols first, I promise you, transitioning to software-based PLC programming later on will be an absolute breeze.
For anyone just starting out, my best advice is to keep it simple. Really understand the magic of normally open and normally closed contacts and wire up a basic latching circuit to see it hold a charge. So what do you think? Are you ready to fire up a simulator and design your very first control circuit? You've got the syllabus, you know the fundamentals, now it's your turn to build the logic. Thanks for hanging out with us for this explainer.